Hello, my name is Alireza Sayahi, and today I'll be talking about security of home networks and Internet of Things devices. With each passing year, smart homes will become more common worldwide and will also face escalating security risk. In this study, I'll be mainly focusing on data breaches, unauthorized access, and firmware attacks, and how we can use this firmware to detect and possibly solve these vulnerabilities. So, smart homes normally offer automation, real-time controls, and personalized environment through IoT ecosystem. For example, smart locks or Google Home that we have in some countries. But these are normally not really that common. And with each passing day, we are going to have more IoT devices across worldwide, which are predicted to exceed 75 billion by the year 2025. As you can see in this chart, by the year 2034, we are going to have more than 40 billion online IoT connected devices worldwide. But the more these devices become common, the more risk and cyber threat they are gonna face. That we need to face and solve them. So, and how we can detect these vulnerabilities? The one of the main ways and the direct ways that we have is firmware vulnerability detection. It is one of the most direct way to protect IoT devices from attack, and it has three main ways to do that. The first one is dynamic analysis. It normally monitors device behavior during runtime to detect vulnerabilities, primarily using fuzzing technique. Fuzzing is a quality assurance technique used to detect coding errors and security vulnerabilities in software, operating system, or networks. It works by attempting to crash a system or trigger errors by supplying a large volume of random inputs. The second way is the static analyze. It analyzes program code without execution, employing techniques like static taint analysis and data flow analysis. So it simply just runs the code without executing the actual thing that it needs to do. And the third one is the binary similarity detection that we will talk later on, because it uses machine learning and normally fuzzy hash algorithm and etc. to find different vulnerabilities. So we have four different type or categories of firmware and four different way of acquiring them. We'll be first talking mainly about type 1 and type 2, which I'll be explaining each one of them. And we'll be talking about every way that we can to acquire this method. The first type that we have in firmwares are Linux-based OS. It normally between 256 to 8 gigabyte storages, and it's mainly used for industrial IoTs. The second time is trimmed Linux-based OS. It's normally between 16 to 64 megabyte storage, and for devices like home routers. The third one is RTOS. It's normally between 16 to 256 megabyte, and for high reliability applications like aerospace or military. And the fourth one is bare metal program. It doesn't have any specific OS, and it only uses simple task loops to detect and do what is tasked to do. We also have four different methods on how to acquire this firmware. The first one is direct download. So for example, if a firmware from a device is publicly on the internet or from vendor channels, we can simply just download that and use it for our debugging. The second way is debugging interfaces. If a firmware has an UART or G tag that we can use to dump file or to dump firmware there, we can use this as well. The third way is the man of the middle, monitoring firmware updates traffic for insecure protocol. And the fourth one is the hardware device itself. We are gonna use the same hardware that we are using flagships that is normally given to the programmer, using different methods to extract what we have in that firmware. In the next part, we have the firmware emulations. Firmware emulations allow us to test IoT firmwares on general purpose computers without physical devices, enabling vulnerability analysis by mimicking the behavior of them. It has three main ways of doing so, which we'll be explaining. The first way is the full system emulation. It emulates the entire firmware and services. It is convenient for testing but has low efficiency. The second way is the user mode emulation. It emulates some specific services. It is more efficient but may have high false negatives. And the third way is the hardware in the loop emulation. It combines emulation with the real hardware, improves the chances but has low efficiency. This way has varied APIs that we can use. It also can include diverse hardware architectures and also closed ecosystems. Some of the main emulators that we have in here are QEMU, Greenhouse, Film AI that have significantly advanced emulation capabilities. So, about the first way that we talked earlier and the second one, dynamic and static analyze techniques, we are gonna be explaining which one, what do we do. Like how I explained before about fuzzing, dynamic analyzers uses fuzzing to fight memory corruption vulnerabilities, for example buffer overflow or heap utilization, and web service vulnerabilities like XSS and CSRF. It has so many different APIs to do that, but some of the more famous ones are 3-Force AFL, as IoT fuzzer, ICPP fuzz, and Firm fuzz. And each one of them uses one of the API that I explained before to detect the vulnerabilities that I'm the furthest. Like for example, 3-Force uses a full system emulation fuzzer based on QEMU, or FirmFuzz uses the device-independent gray box fuzzer Lagrange static analyzers. The second way is the static analyzers that automatically analyzes program code without execution. It's primarily through taint analysis and symbolic explanation, though accuracy remains a challenge. Sometimes it is good and sometimes it is not really efficient to do that. Two main ways of doing so is the static taint analysis that detects sensitive data leakage and it also uses stains like cartoon and detaint. And the second way is the static symbolic execution that combines symbolic execution with program slicing to improve the scalability that we have in our firmwares. The third and the final way that we talked about was the binary code similarity detection. This approach compares binary code to identify similarities and differences. It's a crucial way for vulnerability collection, malware detection, and etc. It has two main ways of doing so. The first one is the traditional approach. It includes fuzzy hashing and control for graph matching to measure structural similarity. And the second one wasn't really possible to do before, but with how advanced our AIs become, it is now possible to use different AIs like Genius, Gemini, Volseeker, Safe, GTrans, and T-Rex to utilize graph neural networks and LPL models to convert binary code into vectors. So we can check how similarities and differences are in different malwares. In this part, we have some security solutions to minimize attack on IoT devices, which are normally categorized into four main areas. The first one is the automatic firmware patching. Always keep your everything up to date is the best thing you can do. The second one is the physical channel protection. Defending us against attack exploiting physical interaction and signal mismatching is important, and you can do that while placing your IoT devices in secure places that are not accessible to different members that you don't want them to interact with. The third one is the sensitive data access control. So ensure your everything, your access and your permission are the things that you want them to be. So guests or unauthorized members or outside or anyone that you don't want your devices to be touched upon won't have access to them. And the fourth one is the communication and authentications and securing communication protocol and device authentication, and just don't keep everything and the default that it is. See what you want to do and address the issues that you don't have so you can fix them later. The next and the final part is the future direction in IoT security. With each passing day, we still have some emerging threats and some ongoing challenges that we still have to think of. Some of them are the physical channel attackers, for example, exploiting signal-to-signal mismatch, ultrasonic signal acoustic waves, and out-of-band vulnerabilities like non-functional design flaws in cross-domain interaction. And some of the challenges that we have that are IoT devices limits full hardware emulation that we talked about before, and it's more focusing on general software components. And in the static analysis, we have the integrating AI driving techniques that shows promising the result for future research, and we can use them. And in the end, future studies will perform an edge for us in the future, so we can decrease the chances of our getting any security problems, hopefully in the future. And thank you all for your